And now these models will look more complex, but they're actually more useful than what we have done up to now. So what we have done up to now is something you do in a homework, okay? It looks interesting, has all the aspects, but not what you will do for your research, for example. So we need to start expanding on these simple models. And the first thing I want to expand is, I'm going to come back actually to the earlier model so we can do the evidence maybe next week, the evidence approximation. But I want to expand on this. And you remember when we wrote the likelihood? In the likelihood, the only unknown parameter was W. And we took that the noise was known, right? The noise was defined by that parameter beta. So I want now to make the noise random variable as well, right? So that way we will not need to do evidence approximation and figure out what beta is. We're going to take, the noise to be a random variable. All right, so be prepared for lots of algebra. That when you look at these equations, and I emphasize this, unless you take the time once in your life to do actually these calculations by hand, you're not learning anything. Once you have to verify that these equations make sense. The good news are, to remind myself of the calculations I did on my own to verify, those calculations I was typing them. Because when you type them, you look at them, either they look nice or not, right? In a piece of paper, everything looks wrong. So whatever you need is in the slides, but for you need to actually do the algebra. If you just read them, I don't think it will help you to expand this to any other problem. So let's see what we have. The notation is going to be slightly different because I wanted to keep the notation of the original statistics papers that actually solve this problem. So that way I don't make mistakes on the notation. So the first change in the notation that you will see is that I'm going to use for the variance directly sigma squared. So I'm not going to use the precision beta. And the second and only change is my design matrix, instead of capital phi, is going to be capital X. No other change. Okay? So capital X is going to be my design matrix. And actually, I suppose using a capital X notation makes sense if your regression function is of the form W transpose X, right? Not phi of X. If it is W transpose X, really, this capital of X takes all the input vectors X's in a matrix form, so it makes sense to use capital X to notate that. All right, so the likelihood, the way that you see here, there is absolutely nothing new. The only thing that I am using from now on consistently is I take the likelihood of the endpoints, and I'm writing it as one multivariate Gaussian. And that's something you need to verify, right? Because we have done calculations with the likelihood of each point. We multiply them. So do that process and show me that basically, when you take this inner product of this transpose that, each term corresponds to one univariate Gaussian, basically corresponding to what we have done earlier, okay? But right now, this is a multivariate Gaussian, okay? Has variance sigma squared, the n by n identity in the diagonal matrix, and the mean is X times W. So rather than writing the regression function for each response as W transpose X, I take all the vector of the responses and I write them as X times W. So I write all my responses simultaneously, all right? Very nice. So this equation has nothing different from what we have seen except putting things in a vector form, okay? And the second different thing is that sigma squared now is a random variable, is not constant. So there are two random variables in the parameters, and that's W and sigma squared, and that will make life a little bit more difficult. Now, the analysis we're going to do is not new, has been around for 40, 50 years, and it's in the books. It's actually in most books in regression, will be chapter 2. So it's not like an advanced model, it's just chapter 2. So how, if we're gonna do a Bayesian analysis, we're going to have to put a prior on W and sigma square. And obviously, it would be nice to use a conjugate prior. And what is, I believe actually, I may have mentioned this, but I even mentioned it in the more general case. But what is the conjugate prior? So my likelihood is a Gaussian, all right? So I'm going to need a prior for the join of W and sigma square, and that conjugate prior is a normal inverse gamma distribution. Okay? I know you know about normal distribution. I want to believe you can search on Google about an inverse gamma distribution, but really the joint distribution of W and sigma square is a normal inverse gamma distribution that has all of these parameters. Okay? And what is a normal inverse gamma distribution? If you write this as the conditional of W given sigma squared times some distribution of sigma squared, then the conditional distribution of W given sigma squared is a Gaussian, and the distribution of sigma squared is an inverse gamma distribution. And you notice the normal distribution has a mean W0, has a variance sigma squared times that matrix V0, and the inverse gamma distribution has two parameters, A0 and B0. And if I write this explicitly, if I write that explicitly, you get this wonderful formula with all the normalization terms. And you should never take for granted these normalization terms, because these normalization terms, where do they play a role? Where these normalization terms come to be extremely essential? Model selection, exactly. So these normalization terms are extremely important for model selection, okay? So don't think, oh, they're little constants, who cares? We care, even though for the type of things we do in these lectures, we're not going to bother with model selection, but for model selection, all of these terms are, not this term, but this thing on the front is extremely essential. Okay, so somebody asks you what's a normal inverse gamma distribution? Is the conditional is a Gaussian given sigma squared, and then the distribution on sigma squared is an inverse gamma distribution. Notice the distribution of sigma squared, not on sigma. So we work directly with the variance here. So we have a likelihood, and I want you to verify to be comfortable with this formula. This is the conjugate prior. If you multiply the twos, and I just do the multiplication and combine the two exponentials, I get this wonderful formula on the bottom. All right? And sigma squared to some power that looks complicated, but is very important. All right? So what is A0 in that power is the first coefficient in the inverse gamma. What is D is the dimensionality of W. What is N is the number of points. So nothing comes by accident, right? If you multiply the normalization constants, and all the other terms, this is what you get. No algebra involved yet, okay? We haven't done any calculations. So we have the posterior, right, given in this rather complex formula that fits in one line on my slide. What type of distribution do you think this posterior is going to be? Since I mentioned the word conjugate prior. It will be normal inverse gamma distribution. So it will be exactly like this form here. You can actually see it, okay, the similarity, okay? Now, somebody says, yes, I don't really see it because there is something like this here with one matrix, but here, you know what I have? I have other weird things. W is here alone, and this term looks like that, but I don't know about that second term. So what do you need to do? What's the idea here again? beyond Gaussians, what is the process to bring this? How are you going to bring this to this form? Complete the square. So try with hard work to make this to look like this, where instead of W0, instead of V0, instead of B0, you're going to have some new matrices and some new coefficients, Vn and An and Bn. And I have done that for you. And here is the answer. If you define Vn to be this, if you define Wn to be that, if you define An to be that and Bn to be that, then it turns out, all right, do you see the formula? It turns out that the joint posterior of W and sigma square is an normal inverse gamma distribution given by the parameters Wn, Vn, An, and Bn. And the algebra is on the slide. You just have to do it. If you look at it, right, if you haven't done it once, you will always hesitate and say, there is no closed form solution. I'm going to use some sampling method to play with it. And you will try to submit a paper, and somebody will tell you you haven't read the books yet. Because if there is an analytical solution, right, you should use the analytical solution, because then it's extremely simple to sample from a normal inverse gamma distribution. Okay? So the posterior of W and sigma square has a closed form solution, is a normal inverse gamma distribution that looks like this. Now, for many reasons, lots of times, for example, you may say, I don't really care at all about W, and I'm only interested about the noise, sigma square. So what you will need to do is, you have a posterior for the joint. Actually, you are going to need to marginalize that and integrate W out so you can get the marginal posterior of sigma square, right? So this is a new concept here, right? We have a posterior of W and sigma square, so now you may need the marginal of sigma square. All right, so, and this indicates given the data, so that's a posterior. So you can actually check in the books if you have a normal inverse Gaussian and you integrate W out, okay? The marginal posterior of sigma square, it's an inverse gamma. Straight, result, you can use it as directly. But the marginal posterior of W, it's another distribution that's extremely fundamental to machine learning for regression problems, and that distribution is a student T distribution. Extremely important distribution. So if you, again, you have not seen it, you may want to read a review in like second chapter from Bishop's book or third chapter when he discusses about distribution, so look at Wikipedia. So I am writing without the normalization terms the student T distribution, okay? The parameters are given here, all right? And so one marginal is an inverse gamma, another marginal is a student T distribution. And I give you here the general form for the student T distribution so you can see it, including the mean and the covariance. This nu that you see here is called the degrees of freedom of the distribution, okay? This delta square, written like that, is what is called the Mahalanobis distance. So it's a distance basically weighted by some covariance metrics, very common in defining distance in these statistical calculations. But this is the formula of the student distribution, and this is actually what you get here. Okay? And the derivation, you have to believe me if you want to compute the marginal. I'm just, this footnote does all the job. Effectively, it comes out, if you want to marginalize and get rid of W or sigma square, effectively what you get out, you get the normalizing factors of some known distributions that you can read from tables. So in this particular case, for example, if you integrate sigma square out, or actually the precision, I change variables, it comes out that the calculation involved to get the student t distribution is the normalization factor of a gamma distribution, right? So the normalization factors are essential to actually even marginalize joint distributions. And this is what I have done here. So remember for now, and it is 12:22, and I think the light will go off. Remember that when we start the lecture on Tuesday, Monday when do we teach? I don't remember now. This normal, the posterior, it's a normal inverse gamma with all the parameters fixed, and we do have direct formulas for the marginal posterior distributions. So I'm going to start with those results, and then I'm going to actually make them uninformed results. So I'm going to push them to some limit to get very well-known posterior distributions that we're going to use for practical calculation. We have to make an effort today to complete this lecture on Bayesian linear regression. So what I'm going to do is I'm going to summarize some of the things we're discussing. So we were trying to generalize the model that we had earlier, where the only random variables, the only parameters were W, and now we make the variance to be a random variable as well. So this is a much more realistic model, and that's actually what you will see in practice. And the only change in notation, I emphasize this again from earlier lectures, is the design matrix is denoted with capital X. And actually the notation capital X comes from the fact that you don't use basis functions in the original work that I'm using here. And so this design matrix consists every row from x11, x12, x1d. So it makes sense to call it capital X, okay? Let me go fast where we stopped last time. We wrote the likelihood for a collection of n data points in a very compact way, and I ask you to verify that this is nothing new, okay? So that's the likelihood for n data points. And then we assume a conjugate prior, and the conjugate prior here is a normal inverse gamma distribution defined by these four parameters. W0 is a vector, V0 is a matrix, symmetric matrix, A0, B0 constants, coefficients, and so the normal inverse gamma is basically a Gaussian given sigma square, and then you put an inverse gamma on sigma square, okay? And what I have done is I wrote explicitly the product of the Gaussian and the inverse gamma. If you think this is complex, I'm just saying it is one of the most commonly used priors for W and sigma square in practice. So there is no way you can escape from it, okay? Now, if you multiply the likelihood with the prior, you are getting an equation, nothing, no algebra, what you see on the bottom. And then, in anticipation, because we call this a conjugate prior, obviously the posterior is going to be a normal inverse gamma. So really what you need to do is you need to put the posterior in the form of the prior, but instead of having all these coefficients with W with 0 as a subscript, you will have a coefficients with subscript n indicating posterior after you collect n data points. So here is the answer. Vn is given by this wonderful formula. Wn is given by that, An is given by that, Bn, etc. And the posterior, the joint posterior of W and sigma square, is a normal inverse gamma distribution. And you should certainly verify it, even though the proof is really on the slides. There is no algebra involved, but I strongly encourage you not just look at it, but convince yourself that this is this makes sense. All right. Now, a lot of times, like the previous analysis we did, we only had W as random variable. So someone will say, "Can you tell me what is the marginal posterior of W?" All right. And so effectively, what you need to do is compute from this posterior the marginals in W and sigma square, and the answers you can actually read them directly from you know, everybody knows what are the marginals of a normal inverse gamma. So for sigma squared, it's an inverse gamma, very convenient with the same coefficients. But for W, the marginal posterior is a student t distribution. Okay? For those not familiar with student t distributions, they come all the time in many tasks in machine learning. Okay? They're also being used as robust priors. So, you know, that's something you really need to review. I wrote it explicitly what the form is going to be. It's going to look like that. Okay. And here is the general definition, cut and paste from textbooks for the student t distribution with mean, mu, precision lambda, and degrees of freedom nu. The derivation, by the way, of these marginals is calculating the appropriate integrals, and really I have done them myself to verify what's going on, and the algebra is really one line. All right, so if you have, if you don't even have to actually compute integrals because there is symbolic integrators on the web. So if you go and say x to this power times e to the minus x, they don't give you, obviously, the boundary terms, right? But you can immediately recognize that this integral comes to be a student t distribution. Trust me, that's how I got it. Okay? And you trust it. And easily verify, basically. By the way, when you marginalize, you know that you're going to get these normalizing factors of some distributions. That's how these results come. And in this particular case, to get the student t distribution, you really needed the normalizing factor of a gamma distribution. All right, so that's how you get this nice answer. All right. Now remember, when you do Bayesian analysis, you don't really care about the parameters, right? The parameters is an artificial part of your model, right? We fitted some regression function with the parameters, but really what we care is to calculate the posterior predictive distribution. And so this is how the posterior predictive distribution looks like. So let me introduce the notation first, right? This is my data set so that's where the posterior comes. The curly X is the design metrics for the test input points where I want to compute Y. So I don't only compute here the response for one X curly, but a whole set of those vectors that are defined by the rows of that matrix curly X. Okay, so I'm generalizing this a little bit from what we have done before. So this is what we need. And you know by now the predictive distribution is the likelihood. And you notice I use X curly there because it's the likelihood that the test points X curly. And then times the posterior, which you remember is a normal inverse gamma. And then you have to integrate in W, and you have to integrate in sigma squared. And a typical student would say, I give up, I drop the class. All right? So assuming that you haven't dropped the class already, okay, you're going to have to compute this integral. So can you tell me what is, without looking at any algebra, how do you anticipate to do, let's say, the integration in W? I mean, what would be sort of the expected way to do it? You don't just go and start trying to do an integration in W, right? It looks very complicated. There is W there, there is W there. So how are you anticipating to do the integration in W?
Combine the exponentials, try and complete the square polynomialization.
That's it. Combine the exponentials and get basically the normalization factor of some Gaussian. Okay? Now, you may say, have I cheated when I derived this, because I knew what the answer is? I don't remember. It's very possible. Okay? So basically, I knew how the closing of the square will be. But, if you actually say, look, I'm going to have W minus something transpose times some matrix times W minus that something, you will be able immediately to recognize both the variance and the mean. Okay? And it comes out, surprise, surprise, that basically when you combine the exponentials, one of the terms that you get looks as a wonderful square, all right, with some metrics. So obviously, you can actually normalize this directly. So you're going to get the normalization factor of a Gaussian with this mean and with this precision. And then you're left with this very long scalar, all right? This is actually, you can see it's a scalar number, all right? So you're left with all of this very long thing that doesn't involve W, okay? So if I call this whole thing as 2 beta, or beta is something, some number, all right, just to make algebra easy, you can then start asking yourself, can I now calculate the integral with respect to sigma squared? All right, so the integral with respect to W, you take care of this from the Gaussian. So the integral with respect to beta, with respect to sigma squared, can be done easily, all right? Because if, I don't know why, but obviously it helped me here, instead of integrating in sigma squared, I change the variables and I integrate in the precision lambda, and I get an integral like that. And an integral like that, it reminds you the normalization factor of what? I mean, you have lambda to some power and then e to the minus beta lambda. A gamma distribution, okay? And then so you will get basically a normalization factor, which actually will be beta to this thing. And done. You basically take care of the closing of the square, you get rid of W, you integrate in lambda, and then what you get is a wonderful thing that looks like this. And when you look at that, what distribution does it remind you?
Student T.
Student T. Okay? Done. So I mean, you have a very close, nice form solution for the predictive distribution in terms of a student T distribution. And there is an exponential here. There is an inverse matrix you have to compute to do these calculations, okay? And I give you a simplifying result using the Woodbury formula. By the way, I have no idea why it hasn't come this before, but the Woodbury formula is fundamental to every matrix inversion in machine learning, in Gaussian processes, everywhere, okay? So I just gave you a simplification. If you want to invert this, is given by this nice, wonderful formula. Okay, and you can click and read about the Woodbury formula. Okay, so the predictive distribution is a student T, and immediately you can see the variance at least has two terms. One has to do with the noise in the data, and another one has to do the uncertainty in the parameters of the model. So the two things together, they give you a predictive distribution for Y. Okay, let me see what was on this previous slide. All right. Now, we're going, did I jump too many slides? No. All right, so now we're going to try to push this generic prior, this inverse gamma, to some uninformative limits and get priors that statisticians love, all right? And they use all the time for doing machine learning. So, so I remind you the prior that we started, normal inverse gamma, all right? So we had these four parameters that were defining a normal inverse gamma. So we're going to push them to an uninformative limit, okay? Remember, a Gaussian uninformative limit means make it huge variance so it looks like a uniform distribution. So we're going to try to make it maybe an informative first in sigma squared, then maybe an informative in W, maybe an informative in both W and sigma squared, right? Because that way we may be able to use the previous formulas and come up with the answers right away without doing any algebra. So let's see how we can do this. So we're going to set, if you look at the inverse gamma distribution, you know the uninformative limit is A0 equal B0 equal to 0. Okay? So we have an uninformative prior for sigma squared. And I am going to, and here is where things will get interesting. I'm going to put W0 equal to 0. And I'm going to set V0 to be some constant g times x transpose x inverse. So what I have now is an uninformative in sigma squared, but I'm going to take a very particular case for the prior on W by selecting the mean to be 0 and by selecting V0 to be some constant. That's why this is called the G prior, some constant G, x transpose x inverse. Now, immediately you can jump and say, wait a second, how can you have a prior that depends on the data? Well, in life, you know, for every rule there's a violation. Okay? And actually, you know, when we discuss about uninformative priors, you know, using Fisher information, we notice that there is the priors coming from there depend on the data. Okay? So V0 is selected to be x transpose x inverse. Okay? And in some sense, if you think about x transpose x is a fundamental matrix that comes in least squares, right? So obviously you anticipate maybe by using this prior, things will get very nice at the end of the day, right? But it's not a matter of getting nice, it's a matter, do they actually work? And surprisingly, they do, okay? So, again, only an informative on sigma squared by taking A0, B0 equal to 0, and then W0 equal to 0, and V0 equal to this, okay? And so if you plug in all of this in the normal inverse gamma, because that's from where we want to come up with these uninformative priors, this is how this normal inverse gamma is going to look, right? So instead of that matrix is going to be this, here is going to be 0, 0, and you can actually show that the posterior is invariant to the scaling of the inputs. All right, so if the inputs x are in meters and you change it to centimeters, the posterior remains invariant, which is a nice property. All right. I am not going, you can read this particular slide, right? But you can see, I am going to derive, I think 1 or 2 slides from now, that the variance of the posterior, it comes out to be x transpose x. All right? So you can actually see now why people use g equal to n, and the corresponding g prior, they call it a unit information prior. Because if g is equal to n, the variance for the prior becomes 1 over n, which is, I mean, if you write this variance as n over n, you can see the prior is equivalent to 1 data point, basically. You don't need to understand this sort of explanation physically, but somehow I want you, if you look at the word unit information prior, implies the selection g equal to n. Right? That's the only thing I care. Okay. So let me keep going now to different type of uninformative priors. So what I'm going to do is I'm going to try to start making the prior uninformative in W as well. All right? And you remember, if you have a Gaussian, to get rid of that exponential in the Gaussian, you really have to make the variance as large as possible. Okay? So it looks like uniform. So what you're going to do is, we're going to select, as before, A0 equal to 0, B0 equal to 0. So it's an informative in sigma square. We're going to still take W0 equal to 0. But this matrix V0, to get rid of the exponential, we're going to basically make it very large. All right? So we're going to have very large variance. So effectively, if I can plug in all of these things, the new uninformative prior is going to be this Gaussian times this inverse gamma. And if you plug in actually all the numbers, all right, it comes out that this uninformative prior is sigma to minus d plus 2. What a weird number. D is the dimensionality, is how many variables W you have. Okay? And where do you get the sigma to the minus d? You get basically from the normalization factor of this Gaussian. Okay? And where do you get sigma minus 2? That comes from the inverse gamma with parameters 0 and 0. All right? So this uninformative prior for the joint is sigma to the power minus d plus 2. So if you see suddenly a paper, right, and it's sigma minus d plus 2 with no justification, you know that it comes basically from a G prior that has been pushed on the uninformative limit both for sigma square and for W. And this is what you get. Let's introduce another uninformative prior, okay? Another interesting development. How about if we take the W and sigma square are sort of independent. So the prior on W and sigma square is the prior on W times the prior on sigma square. If you want to make W to be uninformative, it has to be a uniform distribution, is the mean, right? And if you want to make sigma square uninformative, you will get it from the inverse gamma distribution. It will be 1 over sigma squared. So in this case, the prior comes to be sigma to the power minus 2. You see huge differences when you take that sigma square and W are coupled, all right? They're not independent. You get this prior. If you make them independent, you get sigma to the power minus 2. So in some sense, you can think that this is sort of, it's weird, right? But this is what happens. And the question is, can you actually get this distribution from the G prior? And the answer is yes. And I give you actually all the selection of the parameters that will give you a prior sigma to the minus 2. So 0, you make the variance here very large, and you make the coefficient A0 to be minus D over 2. So if you do that selection, this normally inverse gamma distribution actually can lead to this uninformative prior. All right. Now, let me, so before, if you remember, we derived the marginal posterior for W, and we saw that in the general case is a student T distribution. So what I want to do is I want to take actually that student T distribution for this posterior of W and see how it looks like on the uninformative limit. So as the uninformative limit, I'm going to take this limit. So I'm going to take a prior that is sigma minus 2, okay? And I remind you how we got this. Basically, the only assumption is independence in W and sigma square, or the selections of the parameters that you see here on the bottom, all right? If you select those parameters, you get sigma minus 2. So if you plug in everything in, okay? So if you plug in 0 minus D over 2, this very large, the mean 0, if you plug in all of these things in the formulas we had for the coefficients that define the marginal posterior of W, you're actually, I have the derivations on this slide, you can show that Vn becomes X transpose X inverse, the mean Wn becomes the MLE estimate, AN becomes N minus D over 2, and Bn is given by this nice formula. So if you plug in all of this together, the marginal posterior of W, it's a student T distribution centered around the MLE estimate, very easy to compute, and the variance is S squared divided by N minus D times C. What is my C? My C is here, all right? So my C is nothing else but X transpose X inverse, okay? So directly computable from the design metrics. And S squared is a scalar, and very easy to compute. One line, Y is my data minus X times the MLE estimate, transpose Y minus X MLE. So basically what you have is, you have a distribution, it's not a Gaussian, it's a student T, but has a very nice mean and a very nice variance. Which means, if you actually want to compute confidence intervals on W, you can do this in a very straightforward manner. All right, so if you want to compute plus minus 1 standard deviation, you can use this, and immediately for each coefficient Wj, you can say my estimate is the MLE plus minus 1 standard deviation. Sort of like the way you would do in a Gaussian. Slightly different, but very close to that. Now, why is this important? Because this marginal posterior of W can actually give you hints which W parameters are essential for predictions. And what I mean with this, imagine that you have a problem where, in this particular case, the dimensionality of the input vector x is 100. There are 100 variables, right? Do you actually need all of them? Because, lots of them are correlated in some weird way that you don't know, but you have 100 parameters. Do you need all these 100 parameters? Okay? And so can you think of if you can actually compute the mean of W, the marginal posterior plus minus one standard deviation, can you think a way that somehow you can select which W's are actually needed, so which variables are needed and which they are not needed? I mean, how will you go about this? There are multiple ways, but using just the error bars from W, can you think of one way that you can say, this W and the corresponding input variable is not needed? So remember, for each coefficient, we can compute the mean plus the confidence interval, right? This is really the confidence interval from there. So if you look at the confidence interval and the mean of W, can you make a decision if the particular, let's say, Wj is needed or not? And remember, Wj multiplies the input variable xj. Can you look at it and say it is needed or not? And I have here a very particular example that is part of a very lengthy homework that I will not give it to you, but is most probably the most useful homework I ever use in my class when I teach anything in machine learning. But can you look? So these are the coefficients, all right? And this is basically the confidence interval, and there are some stars next to it. Can you guess how we select which variables are important and which ones are not? So look at all of these variables, right? We have compute W0, W1, and the confidence interval goes from minus 0.08 to minus 0.01. This goes, etc., etc., and then you can see the confidence interval goes from minus 0.31 to 0.67. So how can you make a decision using these confidence intervals alone to figure out which variables are needed and which are not?
If it includes 0, then it's not significant.
If it includes 0, means there is a high probability, obviously, that this hits 0, so it is not needed. If it is either on the negative side or in the positive, then this is needed. Now, if you do this lengthy homework, and anybody who's interested, you can click it from there, or you can search on my website and find this homework. You will see there are 5 other methods to actually compute which input variables are needed, which are essential, and you will find that most of the methods agree. So this idea of working with the confidence intervals is not bad. It gives you the same answer, for example, if you use Bayes factors. And the way you would be calculating Bayes factors for this problem becomes, and do model selection becomes extremely nice, but we will leave this for another discussion, okay? So again, the fact here is that we have managed to compute the marginal distribution of Wj in a very nice closed form solution, extremely easy to compute, okay? And there is something else that maybe it's irrelevant unless you have taken a course on non-Bayesian, on frequency statistics, that this result that you get for this marginal, it comes to be a result that people in non-Bayesian statistics also get from a completely different setting. So 2 different words, somehow they give you the same equation with completely different interpretations, but the equation is the same. Okay? All right. So we're done. Okay, so we're done basically with this sort of example, and obviously, how you select other methods for selecting the input variables that are essential. computing Bayes factors, doing model selection, using the evidence approximation, etc., also need to be added to whatever we have done up to now. So I'm going to try to go to the evidence approximation, but using our first model when we started the lectures, okay, using a Gaussian prior and a Gaussian likelihood. And so we'll see where that, how evidence can come for that model. Okay, so I am going to jump to slide 29. Okay? And I'm going to remind you first what the earliest model was, the simplest model of all. You remember we had a scalar output that we call it y or t, all right? Beta was the noise in the likelihood. We introduce a prior, which is spherical around 0 with a Gaussian, with a precision alpha, all right? And I think we discussed, at the time we said, okay, let's select what alpha and beta will be, but to do this rigorously, we're going to have to compute some optimal values of alpha and beta, and the only methodology we know on computing optimal values of alpha and beta is the evidence approximation. Okay, so I want to formally do the evidence approximation for this regression problem. And by the way, for the problem that you saw before, somewhere in one of my slides from one of the courses, you have the whole slide on, and the program for doing the evidence approximation for that as well. But here we're going to try it for our simple Gaussian likelihood, Gaussian prior model for the evidence. Okay, let's start. So I am going, what I have done on the first equation, I have written down the predictive posterior distribution. And I don't indicate the test inputs, right, because I want the equations to look uncluttered. So this ball T is my training data, and this at ball T is my prediction of some new test inputs. Okay? So remember, the predictive distribution, what is it? It's the likelihood. You agree? The likelihood is only a function of the noise variable beta and the coefficients W. I give you actually the equation on the bottom. And then what is these two things together? It's actually the prior, I'm sorry, is the posterior of all the parameters. So it's the joint posterior of W, comma A, comma beta. And how do I write that posterior? I write it as the posterior of W given A and B times the posterior of A and B. We didn't have this before because A and B were constants, you remember? But right now, I have to plug in the posterior of W and A and B, and I use the product rule to write this as the posterior of W given AB, which we know what it is because this is what we did in early lectures last week, right? Times the posterior of A and B. And of course, we have to integrate all the parameters out, we have to integrate W, we have to integrate A, and we have to integrate B. Okay. Now, remind me, what is the whole idea of the evidence approximation? We keep saying, right, that doing this integral with integrating the hyperparameters is too complicated. So what do we do? What is the idea of the Bayes method? Rather than integrating the parameters alpha and beta out, what do we do?
Use a point estimate.
We will use a point estimate. And in principle, that point estimate, because in this equation here, we have a posterior, right? It's like assuming that posterior has become like a delta function center at some point that we denote here as alpha hat and beta hat. So if you actually plug in this as a delta function around alpha hat and beta hat, immediately you get rid of the integration alpha and beta, and our predicted distribution looks like this, right? And you notice alpha and beta have been fixed to some values that need to be computed. But at least they are point estimates now. They are not random variables, they're point estimates. And this method, very fundamental to everything Bayesian, okay, goes with multiple names. To make things easy, we call it the evidence approximation, empirical Bayes, type 2 or generalized MLE calculation. I think somewhere there was a slide that had all the different methods, but basically this is the evidence approximation. So now we have the difficult task of figuring out what is alpha hat and what is beta hat. All right? So, so remember what, the idea was we had the posterior of alpha and beta, right? So the posterior of alpha and beta generally is written as if I use basically Bayes' rule, this is like a likelihood term times the prior. Okay? So what, obviously I'm going to give you a methodology to compute alpha hat and beta hat, but looking at this equation, I am going to assume that the prior on alpha and beta, it's an uninformative uniform prior. So effectively, the point estimates alpha hat and beta hat that maximize this posterior, they are not any different from the point estimates that maximize the marginal likelihood. Can you see that? That's why we call this marginal likelihood method, right? Because if you make this to be uniform, then to find to find the map estimate is the same as maximizing the marginal likelihood. And you may say, why again I call this marginal likelihood? Because in this likelihood term, there is no W. The W has been integrated out. So to be able to actually do any calculations to find what alpha and beta are all about, we're going to have to bring W back in the picture. Otherwise, we don't know any equations that will allow us to calculate this marginal likelihood. And here's the formula. If you want to calculate the marginal likelihood, you can actually write this as T comma W given A and B, integral W, and then you can actually write product rule as T given W times the prior of W. This is like the likelihood in the denominator of Bayes' rule, okay? So the marginal likelihood, which is about the posterior of alpha and beta, is a product of the likelihood, all right, given W times the prior on W. And we know everything. The prior of W is a spherical Gaussian around 0 with some non-precision alpha. And this is a Gaussian. And I remind you the nice formula. And remind me, what is ED? E with subscript D. It comes from the likelihood. So what is E subscript D? It's an error function that involves what? My training data T minus what the model tells me. Right? Is that square error of the model, from the given training data. We call it ED. Okay? So, so to be able to actually maximize this with respect to alpha and beta, we're going to have to compute this integral in W. And you may say, well, integral in W, I don't know about these integrals. W can be million dimensional. How do I do it? It's trivial. This is Gaussian, so what do you need to do? Close the square. If you close the square, what are you going to get? You're going to get the normalizing factor of a Gaussian, which you can write it down. There's the answer. Very easy. So let's do that. So this, the posterior, which is equal to the marginal likelihood, is equal to this wonderful formula. So I want you to tell me now, where is this first term comes from? This comes from the normalization of, look again here, there is likelihood and prior. So where is the first term comes from? The normalization of likelihood. This comes from the normalization of the prior, and the two exponentials are combined to one error function, that now I put it all nicely together. This is the error function coming from my likelihood model. And beta, if you remember, is the precision. So in the exponential, it's up there, right? And then alpha is the precision of prior, so it's up there as well. So I have combined basically this data error function, if you like, with the regularization term that we had in W coming from the prior. Now, out of magic, without actually doing any algebra, this error function that you see here, I can write it with this wonderful formula like that, where A, it's really the Hessian matrix is the second derivative of this error function. So can you tell me why this error function can be written like this? I remind you, Mn is the mean and the mode of the posterior of W. So why I can write this without even bothering about it directly as equal to this, with no approximations? I mean, you notice here this equation, right, is quadratic in W. So why is this exactly equal to that? What is missing from this equation? It looks like a Taylor series expansion to me, but what is missing? And why it's missing? Being able to talk about these things is substantial, right? Because if you can only do algebra, it doesn't help. So why the first derivative is not there? What is Mn by definition? Is the mode of? Is the mode of the map estimate. And how do you get the map estimate? By doing what to this error function? To this error function on the top? By minimizing it. And the derivative is what? 0. All right? So without doing any algebra, I can write down directly that this error function is Mn. So the error computed at the map estimate plus this nice quadratic term, where A is given by this nice wonderful formula that is basically the Hessian, the second derivative of the error function. Obviously, somebody will say, "Ooh, this looks like a Laplace approximation." Well, it looks like, but it's actually exact. There's no approximation there, right? Because the error function is quadratic. The first term is missing because we're expanding around the mode. So, and in the mode, the derivative is 0. Okay? All right. So, you plug in this error function, the new formula that I gave you. So you're going to get exponential of minus c computed at Mn. And then you're going to have this nice integral that involves W. So what are you going to do with that integral? Do you know how to compute it for me? Do you know how to compute that integral for me? Without doing any algebra. Just looking at the slide and say yes. That integral is the normalization of a multivariate Gaussian, and there is the normalization, right? This is the determinant of the Hessian. We're done. So the marginal likelihood, all right, is given by this normalization factor times this times e to the minus e mn times this from this exponential normalized times the determinant of a minus 1/2. And if I take logs, there is the log evidence. Done. Sort of. We have a closed form solution for the evidence. Okay? And it doesn't matter what problem you have, if it is classification, regression. Most of the problems in computing the evidence, the algebra looks always the same, and always you get normalization constants, right? Because I gave you the general formulas for doing this. And you see here the normalization constants can be complicated because you have the log of a determinant, right? The log of a determinant. So, you know, obviously, things are not necessarily trivial to do the algebra, but this formula is trivial. And I say they're not trivial because what does this metric say? If I go back, right, A involves both alpha and beta. So now you remember you have to optimize this with respect to alpha and beta, but alpha and beta are inside the determinant.
That last term in the yellow, is that supposed to be an m over 2?
Uh,
Line above, next to ln.
yes, I see. This term here, right?
Yeah.
Yeah, looks like. Okay, because I see. Let's be careful here, right? I see. Okay, so I have n over 2 log of beta. So we have to be careful, right? Because I want to believe that lots of the possible typos have been eliminated. I see a 2 pi to n over 2, and another 2 pi to m over 2, and another 2 pi to m over 2. So I think it's right. Okay? But please, if you see something, let me know. Okay? Because sometimes, I look before I come to teach, right? And I say, this formula doesn't look right. But I hesitate to go and change it because you don't change things by suddenly saying it's wrong. I want to believe that I check it once or twice. All right? Okay, so we have this wonderful formula. All right, so m is the number of parameters and the number of data, and we want to do some optimization. Now you have to trust me, right, that if somehow you want to do this numerically and you want to play with alpha and beta, or even actually, the order of the polynomial, all right? So if you want, to say what order polynomial I need to, what is m, what's the optimal m that I should use to maximize this, you can start plotting this marginal evidence with respect to alpha and beta or mu and find optimal values. In this particular case, you can say that if you plot the evidence versus the order of the polynomial, the fourth order polynomial is actually what fits the data, this particular data set that is under this link, okay? This is what maximizes the evidence. By the way, when you're going to use the evidence approximation, you don't really have to do any cross-validation, you just have to maximize the evidence. It may be a difficult thing to do, but I want to believe that all the tools for doing that optimization problem are already out there. It's a matter for you to find them, okay? All right, so we're not done, all right? So there is a merit to actually do the derivatives with respect to alpha and beta, analytically, because really I want you to look at this problem and figure out why, when we do Bayesian things, why there is no overfitting. Right? The key idea here is that we mentioned there's no overfitting because it doesn't matter how many parameters you have versus how many data you have, because the parameters are integrated out, right? But I want actually to do the derivation to see, if you throw on a model, if you throw 1 million parameters, is the model going to be able to actually compute 1 million parameters given that particular data set? And why there's no overfitting? And so we will see if we do the analysis that somehow the model says, many of these parameters I cannot compute based on the data I have. So what I'm going to do is, through the prior, I'm going to force them to 0. So there will be only an effective number of parameters that the model can compute, and that's how it avoids overfitting. And this effective number of parameters, it is computed automatically by the evidence approximation. Okay? So in all the other models, you have 500 parameters, this is what you need to compute. In the Bayesian setting, there is an effective number of parameters, and the model will figure out what those parameters are, and it will only compute those. Okay? Even more interesting, right? If I only give you, let's say, 10 data points and 50 parameters, the model will still work. Right? Because the parameters are integrated out. So the fact that we have less data than parameters is not an issue. But if you try to do this in any other standard way, it's not going to work. Okay, so let me start doing some algebra. And the algebra, not very complicated. There is no way you can understand it in detail unless you go and you read the notes. Okay, so let me tell you how the algebra goes. I am going to do an eigenvalue analysis of the matrix beta phi transpose phi. So I can simplify the algebra a little bit. Okay? So what I'm going to do is I'm going to compute the eigenvalues lambda and the eigenvectors u of the matrix beta phi transpose phi. I remind you, phi transpose phi, phi is the design matrix, right? Phi transpose phi is what comes in these squares. And the only reason I plug in beta there is because it makes the algebra easier. But notice, if you actually read books like Murphy's book, he is not using, when he does this eigenanalysis, beta is not included. So be careful when you read books. So Bishop has this beta there. Murphy doesn't, but it's basically the same problem. It differs by a schedule. Okay? All right. So, so if beta phi transpose phi has eigenvalues lambda and eigenvectors u, if you shift this matrix by alpha times I, then the eigenvalues will shift by alpha plus lambda I. So the Hessian matrix, we have eigenvalues alpha plus lambda I. All right. So let's start taking derivatives with respect to alpha. I'm going to do them fast, and I trust that you're going to go home and you read the notes. Okay. So derivatives with respect to alpha, and I'm going to start with a difficult term, log of the determinant of A. For those who forgot their linear algebra, right, think that if you do diagonalization of the matrix in its eigenbasis, in the diagonal you're going to have lambda 1 plus A, lambda 2 plus A, etc. So the determinant becomes of the product of lambda I plus alpha. Can you visualize this, right? Because in the eigenbasis, everything's in, you don't have off-diagonal things, so it becomes the product of lambda I plus alpha. So you have a log of a product, becomes summation of these logs, and if you want to take derivatives with respect to alpha, the derivative of the log is 1 over lambda I plus alpha, so you get summation of that nice thing. Nice. Very nice, so we got rid of this derivative. The rest are rather easy, all right? So if you can see here there is alpha there, so you're going to get a derivative, you're going to get m over 2a from this first term. Then alpha also comes in this error function, because I can see alpha there. So you're going to get 1/2 m transpose m. And then, of course, we had this log of the determinant. So if you rearrange things, all right, so you set the derivative with respect to alpha equal to 0, and you rearrange things, you get a wonderful equation that looks like this. Alpha times m transpose m. I remind you this is the mean or the map estimate of the posterior, equal to the summation of lambda I divided by lambda I plus alpha, and I call this gamma. There's a reason why we need a new name for a variable. You will see, because it has some particular physical meaning shortly. But what I want you to appreciate of this problem is, usually when you do optimization with respect to a parameter, you say the parameter is equal to this value, all right? Now, unfortunately, things are murky here, because you have alpha here, all right? There is alpha inside gamma. Do we have an alpha in Mn? Is there any alpha involved here at all? Is there any alpha involved also in Mn?
Yes.
Because of that Hessian matrix. All right? So the only way to actually make this to work, and this is again very typical of the evidence approximation, is to iterate to self-consistency. All right? So basically what it means is you assume alpha, you compute Mn, you update gamma, all right? You come back, I have the algorithm actually somewhere, okay? So here it is, you choose alpha, you calculate Mn and gamma, okay? And then you re-estimate alpha, and then you keep iterating until it converges. Okay? Now, if you were doing an optimization, right, you can use an optimizer to do all of these things for you, but actually I want to use these formulas in some sort of analytical manner to figure out, are these equations just another set of equations, or they have some meaning that may be useful to interpret things in Bayesian machine learning. So we would like to do that. All right. Before I finish and go to that physical meaning, let me also say we need derivatives with respect to beta. Okay? And so our eigenvalue problem, all right, looks like this. So effectively, we're going to have to find derivatives of the eigenvalues lambda I with respect to beta, but you can see that lambda I is proportional to beta. There's no beta involved in the design matrix phi. So basically, the derivative of lambda I with respect to beta is really lambda I over beta. So that makes life very easy. So if you take all the formulas where there's beta, so there's beta here, there's beta there, there's beta there, and you take all the derivatives, you come up, there's no algebra, it's just, I put all things together. You come up with this wonderful formula on the bottom that I want you to look left, right, straight, upside down, and tell me what does it look like, or what does it, is it an interesting formula? Does it have any significance? So basically, what is that summation there? Have we seen that before? This tells you how, well the model does in fitting the observations Tn, right? And certainly, you remember early on in the, when we started Bayesian analysis, if this gamma was not there, what is this answer? So yes, that's the sample variance actually, and this particular beta that you get with this formula is what beta? So when you write down the, you compute first you least squares and then regularize these squares and you get the map estimate. What is this? So when we do actually maximum likelihood estimation, what is this formula? What did it gave us before? 1 over n times that, so the sample variance was giving us the sample what? The sample variance is what? How do we call this estimate here? When we wrote the likelihood, right, we had to maximize the likelihood with respect to the parameters alpha and beta. So when we took derivatives with respect to beta, we got this same formula, but instead of gamma, it was 1 over n. So that beta with 1 over n is what? It was the MLE estimate of beta. It was the MLE estimate of beta. So now that we're fully Bayesian, very fully Bayesian, right? We don't have 1 over n, we have 1 over n minus gamma. Now, remind me, so when you compute the MLE estimates, think of a Gaussian for the mean and the variance, right? Are those unbiased estimates? I mentioned this in a lecture. Like if you take the mean and the variance, in our case, really the likelihood was Gaussian. So if we take the mean and the variance, are those unbiased estimates? If we take the MLE estimate for the mean and the variance, are those unbiased estimates?
It's biased. It's biased. Not the mean of the variance is unbiased.
So which one is unbiased?
The mean is unbiased.
The mean. All right. So the variance. So the variance was biased because it was written with respect to the MLE estimate of the mean. Okay. And if you want to make the variance for a Gaussian, if you want to make it unbiased, instead of using the variance to be 1 over n times this error, what do you usually do to make it unbiased? Anybody knows from statistics?
1 over n minus
1
1.
over n minus 1. Okay? And the statisticians will tell you, you put 1 over n minus 1 because that 1 degree of freedom has been used to fit the mean. Right? So one of the parameters was calculated properly, right, by the data. So you have to subtract the parameters identified by the data. So now if you look at this formula, potentially what's the meaning of gamma? So in the Gaussian, right, we had to remove 1 degree of freedom because this is what the data used to fit the mean. So if we have 1 minus 1 over n minus gamma, what is gamma? Potential. And usually intuition is always correct.
The number of degrees of freedom?
The number of degrees of freedom, but complete the sentence. So it's the number of parameters that, continue,
You need to estimate.
well, we have to estimate n of them. So gamma is the number of parameters that the model can identify from data. So basically it's the effective number of parameters. You remember in the Gaussian, you can only really identify the mean, right? So here, you can identify gamma parameters. So gamma is the effective number of parameters that can be identified from the data. And what happens to the other number of parameters, m minus gamma, basically the prior is going to push all of them to 0. Okay? So, so gamma, literally, okay, if I can find the formula, all right, so this is our formula for gamma. All right, so this I is over all the parameters from 1 to m. So look at this and try to use your intuition, right? So if, so let's look at lambda I over lambda I plus alpha. Okay, lambda I over lambda I plus alpha. If lambda I is small, how much is lambda is very small? What is the ratio of lambda I over lambda I plus alpha? If lambda I is small, what is, lambda I divided by lambda I plus alpha? I mean, we're doing approximations now.
Close to 0.
Is 0. So, all right, is 0. Now, remember that lambda I is what again? Remind me, what is lambda I? The way we introduced it, right? It was the eigenvalue of the phi transpose phi matrix. All right? Now, I don't see the formula here for, no, actually I do. Nice. All right? Look at this now. And again, don't bother with constants, okay? So, no, actually I don't see it. No, because that's the mean. So how about if I say, right, when you look at the formula for the variance of W, all right, and you look for the variance of W in different eigendirections, so I'm thinking now that somehow we are looking at the different eigen, we represent things not in direction 1, 2, 3, but in U1, U2, U3, etc. Okay? So if you look now, so you told me, let's say, you told me that lambda I is very small, okay? So if I look at the variance of the W corresponding to the direction I, there is, if you look at that variance, there is a phi transpose phi inverse. So that variance is then not proportional to lambda I, but it's proportional to what? So in the variance of W, right, in that direction, you have phi transpose phi inverse, right, plus alpha. So if you take alpha to be 0, so you have phi transpose phi inverse. So in that direction, what's the variance? Proportional to? It's inverse.
1 over lambda.
1 over lambda. So if lambda is very small, the posterior variance in that direction is very big. And if the variance is very big, it's like the model says, I cannot give you any value, right? I'm not certain about this. And that's when the prior comes and actually makes it to be 0. Okay? So I gave you this actually without the schematics that they are in the slides, okay? But more or less, I know if I go through the schematics and the details, you will get confused. So what I want you to know is somehow this evidence approximation is able to automatically select for you the number of effective parameters. That's why there is no overfitting. So you can actually use 1,000,000 parameters even though you have 10 data points only. The model doesn't care, all right? It will tell you what is the effective number of parameters for your data set, and that information in our regression problem is included in this coefficient gamma, okay? So the gamma gives you the number of effective parameters, and I want you to remember that these parameters that cannot be identified are parameters where the posterior variance is very large, okay? And actually I can give you without any further discussion on the matter, right? I can actually give you a schematic, okay? So if you take contours of the likelihood, all right, and you parameterize the contours so that this axis is U1, the eigenvector U1, and this is the eigenvector U2, etc. And this is your spherical prior, you can see in the directions where the variance is large, all right, the MLE estimate is pushed to the map estimate that is approximately equal to 0. Okay? And I actually give you the formula, all right, if you want to collect the MLE and the map estimate. So if lambda 1 becomes very small, this becomes 0, and the map estimate gives you 0. Okay? Now, to be able to understand these few slides, you need to liberate yourselves from writing equations in matrix form and vector form, right? And write them in terms of components, but in the eigenbasis. If you do that, the algebra becomes extremely trivial. I can even actually look at this nice equation here and immediately tell you, this is the map estimate, right? This is the MLE estimate. I can immediately tell you if I want to take, let's say, a component of the map estimate in an eigen direction, it will be, you can see from here, you have beta times phi transpose phi, so it will be an eigenvalue, all right, divided by alpha plus another eigenvalue, which is lambda 1 times the MLE estimate. I can do magic, okay? You just need to liberate yourselves from this. Now, there is another way that I cut and pasted from Murphy's book, right? You can come up in the same conclusions using singular value decomposition. So if you take the design metrics and you do singular value decomposition, you effectively, you come up with the same conclusions as what I showed you up to now. All right. So now we have computed the evidence with respect to alpha and beta, right? If I can find the plots actually that the students did in one of their homeworks. Give me 1 second. All right, so if you want to do this numerically, all right, you can plot the evidence, the log evidence, versus the log, let's say, of the parameter alpha for a fixed beta, and you can see there's a very well identified optimal for alpha. Now, for reasons I don't know, if it has to do with a particular problem, if the students who actually work on their homework on this, last year, I think, or 2 years ago, they told me when they were trying to do simultaneously optimization on alpha and beta, somehow the iterations were not converging. Okay, so again, I don't know if that is true or not, right? Because here I see a very well identified alpha hat that maximizes the evidence, but the results I have in the lectures, basically they fix beta and they optimize alpha, and then they fix alpha and they optimize beta. Okay, so that works, but I was told simultaneously iterating to compute alpha and beta, it was not working as well. Now, as I mentioned, and you can find the results in Murphy's book, in his toolkit, the MATLAB toolkit that he has. If you try to solve this problem and select alpha and beta using cross-validation, you will actually get the same results as maximizing the evidence. Okay, more or less the same results, but you will see the computational cost playing with the evidence is way less, and the method is more elegant, right? Cross-validation is like, you're doing too much, not using all the data for the analysis, and so it's not something that, it's not Bayesian, basically, but you may want to do that as well. Okay, it's 1:39. You know what? It's a long day, so I'm going to stop there.